Hi everyone, my name is Mike Stamm. I'm Sales Manager for Varex Imaging, typically responsible for flat panel detectors like many of you know, and tubes that we also sell. And with me today is Hendric Speirschneider. I'll just pass it right over to him to introduce himself to you.
Hello everyone, I'm Hendric, as mentioned, technical sales manager for direct conversion. The photon counting part of Varex Imaging, based out of Munich at the nice Application Innovation Center, AIC, where we run fantastic demos and tests.
So Hendric, maybe just that was a good segue to kind of the first question or to start the conversation. So you say you have a demo and testing center in Munich. You have that partially because we're also facing in NDT and inspection many problems that we didn't even dream of 5 or 10 years ago. So could you maybe explain what some of these challenges are that you are trying to solve or have already solved in Munich with direct conversion products?
Yeah, for sure. So the main topic is speed, and speed in regards of remaining the efficiency of the imaging in terms of contrast and low noise value. So we see a high demand of X-ray inline inspection in 2D and in CT as well, where speed is everything. And with our photon counting products, we really are ahead of that. For example, there is battery CT, which no one has thought about a couple of years ago. The end customer, so the battery manufacturer, is requesting a 1 second CT per unit, which is a big thing. Luckily, there is the technology is available in regards of frame rate and so on to really achieve this 1 second with a quality that is comparable to 20-second or even a 1 minute CT 5 years ago.
Wow. Did I understand correctly? 1 second per battery cell?
Correct. And it turns in 360 degrees or a little bit less in that time. And a number of 400 to 600 projection images is captured in that time.
Wow. So I think that already, it's very interesting because it already sort of touches on, I think, a concept that people have about direct conversion detectors, that they necessarily are line detectors, which is of course not true, correct? Because to capture that much data and that much of the battery cell, you do need a certain area. So maybe can you say a word or two about that?
Detectors are not that huge, but it's fair enough just to capture a corner of the battery. For all those tests, you don't need you will not capture the entire battery. That doesn't really work also in regards of image resolution, because capturing the entire battery, you basically lose geometric magnification. So you move a corner of the battery very, very close to the source, because the demand is somewhere between 25 micrometers to 50 micrometers in image resolution. And by only capturing the edges where you have the anode-cathode overhang, this is definitely sufficient for all the measurements. You do not require a huge detector, like a 20 by 20 centimeters, and 5 by 20 is fair enough.
In fact, probably if you're doing some magnification and you have too large of a detector, you've got a parallax effect problem as well, correct? Because we're trying to separate, at least in 2D, the anode from the cathode, and you cannot really afford to have your X-rays come in at too much of an angle as opposed to straight down, right?
Very, very true. So with CT, parallax is you need parallax for CT, but in the end, it's gone after the reconstruction. That's the beauty of it. But in the 2D world, where we use our detectors as a line scanner, we have the huge advantage that by scanning we lose the parallax impact in one dimension. And if you orientate the product or sample properly, then you have a straight shot through the anode and cathodes for upcoming measurements.
can you say, for example, how large a typical detector and what it's called would be that you use to inspect a battery in CT?
In CT,
areas, right?
In CT, it's a THOR detector. The size is pretty much 20 centimeters long and 5 centimeters wide or high, however you want to call it. The physical pixel pitch is 100 micrometers, which is pretty good for such applications, where in the past 200 or even 400 micrometer pixel pitches were used to somehow be fast. So 20 by 5 centimeters THOR. And one more thing, because we have a huge amount of images being captured, those need to be transferred. So the transfer actually, or the readout being the bottleneck, we do have a 10G interface since this year, and this basically solves that issue.
Hendric, when you mentioned before the 100 micrometers resolution, maybe 2 questions to that. So resolution is of course also an interesting way to differentiate a DC product from, I would say, other line detectors, correct, and flat panels that are dependent on the scintillator layer to turn the X-rays into visible light and then finally, excite the photodiode. And of course, as most of us know in this business, there is this horrible trade-off we have to make with the thickness of the scintillator and the efficiency. You don't have that problem, correct?
We don't have that problem. So because we don't use we don't convert from X-ray into light via a scintillator, we directly convert it. That's why we call it direct conversion through this material called cadmium telluride. And no matter how thick you make it, the resolution still remains. So the physical resolution of the pixel.
So when you say 100 microns pixel, you actually also mean 100 microns resolution, which is in our world traditionally not the same thing, right?
Correct.
Wow. Okay. That leads to my second question. Is 100 microns the end of the line, or where does it go from here for you guys?
There is still some fantasy here and real projects and prototypes being built up for 67 micrometer detectors, still remaining the same speed and efficiency and all that, which is key, because everyone knows the smaller the pixel, the less sensitive and so on. But this is the big challenge. So the next step is 67.
Wow.
For next year,
at the risk of making everyone super excited, how real is this? Do you have some hardware already? Are we making some images? Where are we?
So yeah, hardware is ready. It's getting ready. So we shipped the first unit to a partner for high resolution CT projects still before Christmas, and hope to get the real product out somewhere in quarter 2 of next year.
So we should have first images in a real system potentially by the end of the year, beginning of next year.
Correct, and that's especially for 2D line scan applications.
Interesting, fantastic. Yeah, that's really great. So basically, this challenge that many of our customers have, when the pixel size gets smaller, they still need the efficiency, because also usually the tube, the focal spot gets smaller, and of course the power goes down, so you're getting hurt both ways.
Correct. It's a big trade-off, left and right of the chain all the time.
Yeah. So we can avoid at least one of those trade-offs, which is a fantastic advantage. So great.
But to mention one more application, it's not just batteries, it's also electronics, where we see huge demand on speed, like finished goods like laptops, consumer phones, and so on, which where an entire scan is being processed for quality assurance and so on. This is, here we're talking about 500 millimeters per second up to a meter and more, with a nice, sharp, clean image.
I recently posted something on LinkedIn. I think that was part of a laptop, that an image you guys made. So you're really scanning entire closed laptops in one go.
So our customers, the system integrators, scan those, yeah, with a fairly long camera, so 600 millimeters or even longer,
Wide,
to ensure that you can scan it in one pass and not with several passes and then stitch it together. So it's a one pass inspection of a fairly huge good, yeah.
So Hendric, what do they do with the image? Like what is a end user, you know, like, I don't know, let's say Dell or Apple or whatnot, what do they use this data for a completely assembled product? I'm just curious. What's the application?
I mean, they basically look for that all parts are properly inserted on the correct location. They look for items that are not supposed to be in that unit, which is I believe it's the main thing.
And so again, because you can offer this extreme scanning speed and still get very good contrast, you can actually get into the line and inspect parts really as they 100% as they flow through the line.
That's always the key. Yeah, X-ray is always at the end of the line. Therefore, it could be the bottleneck at the end of the line, and the overall goal is not to be the bottleneck and to still have some reserve in speed capacity, so to say.
It's just interesting. I remember when I joined this business now over 10 years ago, I was aware that there were X-ray machines doing inline 2D inspection, but I was always told, you know, they're there because they have to be, because somebody wrote it on a specification from government. You have to inspect all of this with X-ray. We don't really care how you do it, but typically the machines were cheap and not useful.
Yeah, so-called expensive conveyors. That's the
something like this, yeah. Yeah. Whereas here, now we're at a point where the technology is good enough for actually adding real value to the customer.
Yeah, let me ask a question, Mike. You being a sales manager of Varex, so to say, what's in it for the customer now that DC is part of the Varex group? Maybe you can outline that a little bit.
Yeah, that's a great question, and one that we get once in a while. Of course, we buy a company here and there, and then the thing is, well, does the competition go down the tubes, or how does this work? And I think we've now shown with the PerkinElmer imaging group joining forces with us that what it happens is, because Varex is the only component manufacturer worldwide that makes sources tubes for industrial purposes, and
so the entire image chain.
The entire image chain, really from source to detector, including correction software that we now also offer. We truly understand how these things work together and how to make one work very well with the other. So the whole idea we have in Varex Industrial, and that we try to hope we can live by in the next years to come, is 1 + 1 is 3. So we know the source, we know the detector, we have experts that can put the two together. And so the two components, if they're both from Varex, will work extremely well together and give you that 3 result instead of that 2 result. And of course, the same logic applies with DC. So we know the tricks to make a product work really well at 450 kV and work really well at 50 kV, and both need sort of specific treatment, need the know-how. What do you have to put inside? Which material can you use? Which one do you avoid? Do you optimize the product for high energy? Do you optimize it for low energy? Do you make one that fits everything? You know, that these are the topics we try to go in depth with our customers, try to understand what are their needs, and then tailor the product so it fits them and hopefully a whole bunch of other customers as well. So the advantage really of an integration like this is that a little bit down the road, obviously not immediately because it takes time to integrate the engineering teams, a little bit down the road, the customer will get a product that is decidedly better than what it was before. That's the idea.
Yeah, that brings me to a nice example from an application point of view or customer demand is high-speed imaging So super slow motion, where the entire image chain needs to be set up very, very sensitive in regards of communication interfaces and so on. Where the AC can provide a high frame rate, 5,000 frames per second, and more to come in the next quarters. Plus a very powerful source from Varex and the triggering interface in between that makes this a very nice image chain or black box for those applications where you would, I don't know, drop any device and investigate the movement of parts within that device during this drop, for example. But many other applications, of course.
So are you talking about things like, I don't know if we can reference this, but for example, there's a YouTube channel called the Slow-Mo Guys, and all they do is video stuff at 5,000 frames, 10,000 frames per second. You really see what happens. It's kind of amazing in super slow motion as an object shatters or explodes or so a liquid moves, things like this. Because we have an imaging chain now with, I think it's a rotating anode tube, correct?
Oh, correct, yes.
Yeah, so extremely high flux, and you use all that. You can actually put all that flux on the detector, and it'll capture it, and that way you can freeze motion, just to make it incredibly slow. Is that what we're talking about?
That's exactly what we're talking about, and this is available for the normal optical world, video and so on. For sports and nature, science, and wherever it's used, but it's very tricky in the X-ray world. And then now we really have a fantastic setup to achieve that.
Very interesting. So we have, for example, locally here, there's a company in a neighboring town, and they build testing systems for destructive testing. They test concrete and steel and whatnot, put a lot of pressure on it, and basically observe what happens as it breaks. So in theory, what you're saying is that could, in this concrete application, you could have an X-ray system like you're talking about, the black box. You add it to that system, and you can actually see what happens in the sample in that precise moment where it disintegrates.
Not just what happens on the enclosure level, but really inside of it. Yeah, I mean, very down the line or the path, you could imagine if you have a very large detector, which is fast, crash tests for automotive purposes. This is the dream.
What frame rate can we support here? What are we talking about?
We're talking around 5,000 frames per second, and these are a lot of images, and you need power. That's why we need a rotating anode source. Same as in photography. If you want to have very short exposure times, you need a lot of light or flashlights or whatever. In addition, the flashlight is the X-ray source in our case.
And is it similar to high-speed video or photography, where you can, for example, do a 1 or 2 second sequence where you have an extreme brightness, and during that time everything happens, so you don't have the light on the whole time, for example?
No, and this will lead to overheating in the video world as well as in the X-ray world. So we're talking about 1 or 2 seconds, but that's all we are interested in. And in 2 seconds, then you already have 10,000 images plus to investigate. This like more than 10 seconds or 20 seconds of slow-mo. Yeah. So
the detector runs continuously, and then at the right time, you trigger the X-ray source, then you trigger the action. You make sure you capture all the frames, and then you find what you're interested in after.
Correct. It's all about the timing in respect of triggering. Yeah.
Understood. Yeah, that's exciting. That's definitely not something I would say we're used to from the traditional X-ray world. So
no, definitely not.
Yeah. So basically,
you'll see that in the next couple of years, more and more those applications.
So we are with this technology. potentially opening new markets for our customers that simply didn't exist before, right?
Right.
Yeah.
Right.
Yeah, that's great. Yeah, I mean, isn't that what everyone wants, right? You don't want to just incrementally 2-3% here, there. You want to see something new that'll give you an extra 10, 20, whatever.
How do you differentiate which product to offer, to use, and so on? So how do you communicate it to the customer?
So the more, I would say, what used to be the DC team and what used to be the Varex team interact and spend time with customers, we actually also find out ourselves step by step how I would say the two different product lines best fit different purposes, right? So I think maybe one way I always like to look at is sort of looking at it in reverse. Where does it absolutely not make sense to use one product, correct? And for example, if you do need a live image 15, 20, 30 frames per second, that absolutely needs to be, say, 40 by 40 centimeters, at least at the moment, you cannot use a direct conversion detector. Right, so that for example would be a very obvious one end of the scale to frame the problem. Another way to look at it, perhaps, where can you not use a flat panel? So if you need 5,000 frames per second, unless you bin it down to 1 pixel, or you restrict your area to an extremely small area, you cannot use a flat panel. The amorphous silicon technology is simply not fast enough, and even the state-of-the-art CMOS detectors can't do it. So you do need a direct converting detector, not only to get the frame rate, but to get the efficiency you need to not only have noise at 1 millisecond per frame or less. So ultra fast is definitely a direct conversion domain. Fast and very large is definitely a flat panel domain, and perhaps everything in between, there are gray areas, which maybe one is better, one's not. I think what is fantastic about working with Varex as a customer, you can tap into dozens of years of experience of people who are experts at the one or the other technology and now are becoming experts at both. So we feel we can understand a customer's problem very well if the customer offers insight into their issues, and try to solve it with the best possible product. So we don't have the mission, we sell as many flat panels as possible, or we sell as many DC detectors as possible. We have the mission to give our customer exactly the right product so he can move the needle forward. And I think we're very well positioned to do that. We have I think you will agree, Hendric, right? The interaction between the teams is very, very good.
For sure.
And in fact, we often now see it that we go visit customers together, to optimally solve the problem.
One item that we haven't talked about, but which is where DC detectors are capable of, is dual energy. So with one pass, we can basically capture 2 energy levels of the material to help discriminating different materials. You see that a lot in material separation. Recycling is a huge market, and also growing.
As one of the things we work on in Varex right now heavily is the CST, the cone beam software tools, which one of the fillet pieces is the scatter correction and the beam hardening correction. And as we improve that, we really see jumps in CT reconstruction quality. But just thinking out loud here, having that built into the detector combined with the software, again here, you just see the potential we can tap into, right? We're just scratching the surface. Now you give us a new type of data we can use, and boy, it just gets that much better, right?
So the future is the smart detector with add-ons.
Yep.
Not just the raw image, but with processing.
Indeed.
And so on, which then the customer doesn't have to take care of, because this is tricky and needs a lot of resources. Yeah.
The know-how, how it works in depth, the detail, and again, do you use this material or that material? How does it scatter, et cetera, et cetera. So, yeah. I think in summary, one can say this is going to be a very interesting ride. And again, we've got a couple of great teams coming together with the intent of moving the needle forward for the industry and moving the needle forward for our customers so they can solve the problems they have today, but also the ones that are coming in the future, and hopefully crack into some new markets that will show them real growth and being able to do more and more.
Absolutely.